So let's see how to apply this to estimate the covariance of a pose. So first let's review how we solve for the pose of an object using iterative least squares. What we did is we took a bunch of image points, little p, and their corresponding 3D points on the object, big P. So we knew the coordinates of those points in the object's coordinate system, and we wanted to solve for the camera to object pose given by x here. So we also knew how to predict image points given an estimate of the pose x. So given a point P and the pose, we could predict the image location of that point. This function actually returns the entire set of image points given the entire set of object points and the pose. So the way we did this is we took the derivative of each side and got this equation that should look familiar. Delta P equals J delta X, where J is the Jacobian of the function f. And then we solved for delta X in terms of J and delta P. So delta P here now is the error between the predicted location of the point and its actual measured location. And then we found the correction to the pose delta X. We added that to X, and we just repeated those steps. Okay, so now we want to find the covariance matrix of the pose. Since the pose is a 6-element vector, that's a 6 by 6 covariance matrix. So from the iterative least squares fitting, we had this equation giving us delta x in terms of delta p. And I'm going to write it in shorthand as the pseudo inverse of J, like that. So the covariance of x then is the expected value of delta x transpose. So I plug in the values for delta x here. And recall, simplifying by taking the transpose of this product, I get this. And again, because J is not a random vector, I can pull that out. So I get the expected value of delta P transpose, which is just the covariance matrix of P. So little p here, remember, is the image points that we measured in the image. So what we have here is the uncertainty of measuring the image points, and from that we can get the uncertainty in the derived pose. So if the uncertainty in measuring all the image points is independent, then that CP is just a diagonal matrix where all these values are the same. And I guess I should have written that sigma sub x is equal to sigma sub y if there's no difference in measuring the x dimension or the y dimension of the image point. So here's an example of calculating, let me back up here, just using this equation right here on the program that found the pose of the box using iterative least squares. So the derived pose of the box was given by this. The first 3 elements are the angles in radians, and the last 3 are the translation in inches. So the covariance is the 6 by 6 matrix here, and the diagonals are the most informative, I suppose. This coordinate here, this bottom right one, is the variance in the z coordinate. So that's the z is of course the line of sight of the camera, and that is the largest. That's, as you would expect, that's the direction along which the error is largest. Okay, how did we come up with those delta p's now, that uncertainty in measuring the image points? One way to do that is you could do it experimentally by measuring how well you can compute image locations, or you could do it analytically from knowledge of the feature operator and the noise. Another way to do it is to look at the image residual error. So remember, part of the process of computing the pose, we did that by computing the image residual. So we can take the sum of squared residuals, that's the difference between the measured image points and the predicted image points, and we can divide that by 2n minus 6 to get an estimate of our image errors for all the points. So the reason we have 2n minus 6 is that we actually have 2n values here that we're summing, because each image point contributes 2 values. And there are 6 parameters in the pose, so we have to subtract off 6 degrees of freedom. In other words, if we had only 6, if we had only 3 points, there would be no error at all. This shows just a way we can visualize the scene of that box and the uncertainty. We'll be drawing a wireframe model of the box and transforming it according to the pose that was found, and drawing this little solid box for the camera using MATLAB's fill3 function. But then we want to draw the uncertainty here. So recall that we're going to interpret the covariance as a Gaussian. And the place where this exponent is constant is a surface now of constant probability. And it's essentially an ellipsoid. It's the equation of an ellipsoid in n dimensions. So a 6 degree of freedom pose now, we have a 6-dimensional ellipsoid, but that's hard to visualize. So instead I'm just going to extract a 3x3 submatrix corresponding to the translation. MATLAB's ellipsoid function gives us the vertices of an ellipsoid centered at these coordinates with this radius. But the ellipsoid is aligned with the XYZ axes. So we need to find the correct radii and rotate the vertices appropriately. So the way we do this is we start with the equation of the ellipsoid. We want to find a rotation such that if we apply a rotation to our vertices, we would get a ellipsoid that is aligned with the XYZ axes. If we did that, then this equation would become this, where D here would be a diagonal matrix. Or plugging in for what Y is, I would get this here. So if I compare this equation to the one up here, I see that the C inverse is just equal to R transpose D times R. So I just need to find these values of D and R from C. So I can do that by taking the singular value decomposition of C inverse I mean. That yields a diagonal matrix and these orthogonal matrices U and V. And the length of the axis in the ith direction is 1 over the square root of S sub I. Those are the singular values divided by Z squared, where Z, of course, is the constant that I pick here, probably like 3. So this is the MATLAB code that draws an ellipsoid given a covariance matrix C, CZ here. And it finally draws the ellipsoid using MATLAB's surface function, surf here. And let me just go ahead and run this. So this function is called pose. And the first part of it fits a pose using that least squares fitting algorithm. In this case, it took me 7 iterations. It estimated the error per point as 2.1 pixels, and this is the derived covariance matrix. So this is the scene here. Let me actually finish running the program. I'll just rotate it here so you can see. There's the camera, and this is about where we looked at the image from. So I've also displayed the ellipsoid corresponding to the translational uncertainty. That is this little thing down here. And that is actually aligned. Oops, let me back up a little bit. As you would expect, it's aligned with the line of sight from the camera here. And this is some scenes or some images from that paper that shows how to calculate the uncertainty from image projections In this case, we also calculated the rotational uncertainty and displayed that as these cones here. And finally, we showed how to fuse uncertainties from multiple sensors. So given a covariance matrix corresponding to the pose uncertainty for one sensor and that from another sensor, you can combine those to yield a combined estimate of pose that's more accurate than both of them.